On November 23rd, 2023, at two separate locations in the United States, something happened that should not have been possible. In Hanford, Washington, inside a facility shaped like a massive letter L, each arm stretching 4 kilometers across the desert floor, a laser beam split in two and bounced between mirrors hanging in a vacuum. At the exact same moment, 3,000 kilometers away in Livingston, Louisiana, inside an identical facility surrounded by cypress swamps, a second laser beam did the same thing. Both beams had been bouncing back and forth for years, measuring the distance between their mirrors with a precision smaller than 1,000th the width of a single proton. On that Thursday afternoon, both beams wobbled, not from an earthquake, not from a passing truck. Both detectors, separated by an entire continent, registered the same distortion in the same fraction of a second. Space itself had stretched and compressed, pulled like taffy by a ripple travelling at the speed of light from a point roughly 7 billion light years away. The signal lasted 1/10 of a second. In that sliver of time it carried the fingerprint of two black holes, each one so massive that the physics governing stellar death says they should never have formed, spiralling into each other at a significant fraction of the speed of light before merging into a single object 225 times the mass of our Sun. The resulting black hole was spinning at roughly 4 million times the rotation rate of Earth. And the collision had happened so long ago that when the gravitational waves began their journey toward us, our solar system did not yet exist. Nobody celebrated, not right away, because the scientists who recorded that signal could not explain what they had just found. These two facilities are called LIGO, the Laser Interferometer Gravitational Wave Observatory. Together with a partner detector called Virgo in Italy and another called Kagra in Japan, they form a network that listens for gravitational waves, ripples in the fabric of space-time predicted by Albert Einstein in 1916 but not directly detected until a century later, on September 14, 2015, when LIGO picked up its first signal from a pair of merging black holes that produced a remnant 62 times the mass of the Sun. That first detection confirmed one of the last untested predictions of general relativity and earned the 2017 Nobel Prize in Physics. Since then, the network has recorded over 300 gravitational wave events, almost all of them from merging black holes or neutron stars. Each detection tells scientists about the masses, spins and distances of the objects involved, information encoded in the shape of the wave itself, the way a ringing bell reveals its size and composition through its sound. But out of those 300 detections, this one, designated GW231123 after the date it arrived, stood completely alone. The masses were far beyond anything previously confirmed. The spins were near the maximum allowed by Einstein's equations. And both of the black holes that collided fell inside a mass range where, according to over 50 years of theoretical work, nothing should exist. To understand why that matters, you need to understand how black holes are born, and more importantly how the biggest stars in the universe die. A star lives by burning fuel. Hydrogen fuses into helium in the core, and the outward pressure from that fusion holds the star up against the crushing inward pull of its own gravity. When the hydrogen runs out, the core contracts, heats up, and starts fusing helium into carbon. When the helium runs out, carbon fuses into heavier elements. This process repeats, building up layers like an onion, each layer burning a heavier element than the one before. The sequence goes hydrogen, helium, carbon, neon, oxygen, silicon, and then it stops, because silicon fuses into iron, and iron is the end of the line. Fusing iron does not release energy, it absorbs it. When the core becomes iron, fusion stops, the outward pressure vanishes, and in less than a second the core collapses under its own weight. For most massive stars, this collapse triggers a supernova. The outer layers of the star bounce off the collapsing core, or are blown outward by a flood of subatomic particles called neutrinos, and the core itself gets crushed into either a neutron star or if it is massive enough, a black hole. The black hole that forms is always less massive than the star that created it, because a large fraction of the star's material gets ejected in the explosion. This process works cleanly for stars up to a certain mass. A star that starts its life at 20 or 30 times the mass of our Sun will leave behind a black hole, somewhere between 5 and perhaps 60 solar masses, depending on how much material it loses over its lifetime through stellar winds and the supernova itself. The physics is well understood. The models match the observations. Every black hole Merger LIGO had detected before November 2023 fit comfortably within this framework. But there is a problem at the top end, and it is the kind of problem that does not give you a warning sign. It gives you an absence. When a star is very massive, with a helium core somewhere between roughly 65 and 130 times the mass of the Sun, something different happens inside the core before the final collapse. The temperatures get so extreme, above 300 million degrees Kelvin, that the gamma-ray photons produced in the core become energetic enough to spontaneously convert into pairs of matter and antimatter, specifically into electron-positron pairs. This is Einstein's famous equation working in reverse. Instead of matter converting into energy, energy is converting into matter. Normally, this would not be a problem. The electron-positron pairs would almost immediately annihilate each other, converting back into gamma rays, and the core would carry on as before. But at these extreme temperatures, the rate of pair production outpaces the rate of annihilation. The gamma rays that were providing radiation pressure, the outward push holding the core up against gravity, are now being converted into particle pairs, faster than those pairs can convert back. The radiation pressure drops, and when radiation pressure drops inside a stellar core, the core contracts. The contraction heats the core further. The higher temperature produces even more pairs, draining even more pressure, causing even more contraction. It is a runaway feedback loop. In stars at the lower end of this mass range, the core contracts until conditions ignite explosive nuclear burning. The star pulses violently, ejects some of its outer layers, but ultimately survives. It goes on to collapse normally, forming a black hole. These events are called pulsational pair instability supernovae, and the black holes they leave behind have masses capped at somewhere around 45 to 65 solar masses, depending on the specific nuclear reaction rates involved and the metallicity of the star, meaning how many elements heavier than hydrogen and helium it contains. But for stars above a certain threshold, the pair instability process runs completely out of control. The core collapses so violently that the resulting nuclear fusion releases more energy than the star's own gravitational binding energy. The explosion does not just blow off the outer layers, it destroys the entire star. Every atom, every particle. There is no neutron star left behind. There is no black hole. There is nothing. The star is annihilated in what is called a pair instability supernova, and the debris scatters into the interstellar medium, never to reconstitute. This was first predicted in 1967 by Zeldovich Parkat, Giora Rakovi, and Niersak. Their calculations showed that stars in this mass range simply cannot leave behind compact remnants. The physics is elegant, internally consistent, and has been confirmed by increasingly sophisticated simulations over the past 6 decades. The result is a gap. Below about 65 solar masses for the helium core, black holes can form through normal collapse or pulsational pair instability. Above about 130 solar masses for the helium core, stars are so massive that they skip the instability entirely and collapse directly into black holes without triggering the runaway pair production. But between those two boundaries, there is a desert, a mass range, where no black hole should exist, because the stars that would create them destroy themselves completely in the process. This is called the pair instability mass gap. In terms of the final black hole masses, it stretches from roughly 60 solar masses at the bottom to roughly 130 solar masses at the top, though the exact boundaries are debated and depend on assumptions about nuclear physics and stellar evolution. The gap has been a cornerstone of astrophysics for more than 50 years. Entire research programs have been built around it. Simulation codes have been calibrated to reproduce it. When LIGO began detecting black hole mergers, one of the key scientific goals was to map the mass distribution and see whether the gap appeared in the data, and for years it did. The black holes LIGO observed clustered below 60 solar masses, with a sharp drop-off at the upper end, exactly as predicted. Then on November 23rd, 2023, two black holes with estimated masses of roughly 140 and 100 solar masses crashed into each other 7 billion light-years away. Both of them sat squarely inside the forbidden zone. The signal that LIGO recorded did not just break the previous record for the most massive merger ever detected. The prior record holder, an event from 2020 called GW190521, had produced a combined black hole of about 142 solar masses. In that event, one component, at roughly 85 solar masses, had straddled the lower edge of the mass gap and generated significant debate about whether the gap was truly empty or just sparsely populated. Researchers proposed explanations. Perhaps the 85 solar mass black hole had formed through a previous merger of two smaller black holes, a process called hierarchical merging, where the remnants of one collision go on to collide again, building up mass step by step. Perhaps the boundaries of the gap were slightly different than the models predicted. Perhaps nuclear reaction rates had enough uncertainty to shift things a few solar masses in either direction. GW190521 was troubling, but it was not catastrophic. It touched the edge of the gap. It could be explained as an outlier, a statistical fluctuation, a product of unusual circumstances in a dense stellar environment, like a globular cluster, where black holes could find each other and merge repeatedly. GW231123 could not be explained that way. This was not one object at the boundary. This was two objects deep inside the forbidden range, both massive, both spinning at nearly the maximum rate allowed by general relativity. The spins were measured at roughly 0.9 and 0.8 on a scale where 1.0 is the absolute physical limit. These black holes were not just forbidden by mass, they were forbidden by spin. Hierarchical mergers produce remnants with a characteristic spin of about 0.7, and subsequent mergers tend to randomize the spin directions. Getting two black holes that both spin at 0.9, both deep in the mass gap, through hierarchical merging alone requires a chain of coincidences that stretches the statistics past the breaking point. Mark Hannam of Cardiff University, a member of the LIGO Virgo CAGRA collaboration, put it plainly. Black holes, this massive, are forbidden through standard stellar evolution models. Cole Miller of the University of Maryland, who was not involved in the detection, noted that this event does not have a clear and obvious match with any of the major formation mechanisms, and there was another problem. Because the black holes were so massive, LIGO captured only the very tail end of the signal, roughly the last 1/10 of a second before the final merger. When two smaller black holes spiral toward each other, LIGO can record many orbits, sometimes dozens, giving scientists a long stretch of data to work with when extracting masses, spins and orbital parameters. For GW231123, the black holes were so heavy that the gravitational wave frequency at which they orbited was very low, below LIGO's sensitive band until the very last moments. The detectors caught only the final plunge and coalescence. This made the event extraordinarily difficult to interpret. The theoretical models used to extract physical parameters from gravitational wave signals had never been pushed to objects this massive and this rapidly spinning simultaneously. Different models gave slightly different answers. Gregorio Carullo of the University of Birmingham, a member of the collaboration, stated publicly that it would take years for the community to fully unravel this intricate signal pattern and all its implications. The data was real. The detection was solid. Both LIGO detectors saw it simultaneously, ruling out local noise, but the objects it described should not exist. The signal was at the extreme edge of what the models could interpret, and for 18 months after the detection, no one could offer a convincing explanation for where these two forbidden black holes had come from. The signal sat in the data. Papers were written, conferences were held, the theories argued with each other. And then, in November of 2025, a team at the Flatiron Institute in New York ran a simulation that nobody had attempted before. They included something that every previous model of massive stellar collapse had left out. And when they did, the forbidden black holes suddenly made sense. But to understand what they found, we need to go deeper into the physics of how stars die, because the answer was hiding not in some exotic new particle or unknown force of nature, but in something as fundamental as a magnetic field, the kind of thing you see every time you stick a note to your refrigerator. Except at the heart of a collapsing star, a magnetic field can do something that 50 years of simulations had never accounted for. It can change the mass of the black hole that forms, and it can do it by a lot. The idea that certain black holes cannot exist sounds like the kind of thing that would come from speculation or guesswork, but the pair instability mass gap is one of the most robust predictions in all of astrophysics. It does not rely on exotic assumptions about unknown physics. It relies on two things we understand very well: nuclear fusion and the conversion of energy into matter through Einstein's equation E equals mc squared. The chain of logic goes like this. When a massive star reaches the final stages of its life, its core is a furnace operating at temperatures that would be difficult to overstate. Hundreds of millions of degrees. At these temperatures, the photons, the individual particles of light bouncing around inside the core, are not ordinary visible light photons. They are gamma rays, each one carrying enough energy to make things happen at the subatomic level. In a core that hot, gamma ray photons can spontaneously convert into pairs of particles. Specifically, one high-energy photon can transform into an electron and its antimatter twin, a positron. This is pair production. Einstein's equation tells us that energy and matter are interchangeable, and this is one of the places in the universe where that exchange happens routinely. Under normal conditions, the electron and the positron almost immediately find each other and annihilate, converting back into gamma rays. The process cycles back and forth, and the net effect on the star is essentially zero. But when the core temperature crosses a critical threshold, roughly 300 million Kelvin, the rate of pair production begins to outpace the rate of annihilation. Gamma rays are being consumed faster than they are being regenerated. And those gamma rays were doing an important job. They were providing radiation pressure, the outward push that counterbalances gravity and keeps the core from collapsing. When that pressure drops, the core begins to contract. Contraction raises the temperature. A higher temperature produces even more electron-positron pairs, draining even more radiation pressure, causing even more contraction. The process feeds itself. For stars at the lower end of this critical mass range, helium cores between roughly 40 and 65 solar masses, this runaway contraction does not immediately destroy the star. Instead, the contraction compresses the core enough to ignite explosive, nuclear burning. The star pulses. It blows off a portion of its outer layers in a violent eruption, then settles back down. It may pulse several times over thousands of years, shedding mass with each episode. Eventually, when enough mass has been lost, the core falls below the threshold for pair production, and the star collapses normally into a black hole. These are pulsational, pair instability supernovae, and they set a ceiling on the mass of black holes that can form through this channel. That ceiling sits somewhere around 45 to 65 solar masses, depending on factors like the star's metallicity and the precise rates of certain nuclear reactions. The uncertainty in these numbers is real, and researchers have spent years trying to pin them down. But the ceiling itself is not in doubt. it exists. Above this range, for helium cores between roughly 65 and 130 solar masses, the pair instability mechanism is not a nuisance that the star can survive. It is a death sentence that leaves no remains. The core contracts so catastrophically that the resulting nuclear explosion releases more energy than the gravitational binding energy of the entire star. There is no bounce. There is no remnant. The star is obliterated at the subatomic level, its material scattered into the surrounding space at a significant fraction of the speed of light. Nothing is left behind. Not a white dwarf, not a neutron star, not a black hole, nothing. And then, above 130 solar masses for the helium core, something different happens again. Stars this massive are so large that their cores can collapse directly into black holes before the pair instability mechanism has time to build up and destroy the star. The collapse happens too fast for the runaway feedback loop to fully develop. These stars skip the destruction and form very massive black holes directly. The result is the gap. Below roughly 65 solar masses of helium core, black holes can form. Above roughly 130 solar masses, black holes can form. Between those two boundaries, pair instability supernovae destroy the star completely, and the final black hole, mass distribution, has a hole in it roughly spanning 60 to 130 solar masses. The exact numbers shift depending on which research group you ask, what nuclear reaction rates they use, and whether they account for rotation or binary evolution. Some models place the lower edge as low as 45 solar masses. Others push the upper edge to 140 or beyond, but every model produces a gap. The gap is the prediction, and it has been the prediction for nearly 60 years. When LIGO began detecting black hole mergers in 2015, the mass gap was one of the first things astrophysicists looked for in the data. If the gap was real, the distribution of observed black hole masses should show a sharp drop-off, somewhere around 50 to 60 solar masses. Through the first 3 observing runs, from 2015 to 2020, the data broadly confirmed this expectation. Black holes clustered in the range of 5 to 50 solar masses, with a clear preference for the 20 to 40 solar mass range. The gap appeared to be real, or at the very least, the region above 60 solar masses was much more sparsely populated than the region below. Then came May 21st, 2019. On that day, LIGO and Virgo detected a gravitational wave event that would become one of the most debated detections in the field's short history. The event, designated GW190521, involved the merger of 2 black holes with estimated masses of roughly 85 and 66 solar masses, producing a remnant of about 142 solar masses. The 85 solar mass component sat inside the mass gap. It was the first clear indication that the gap might not be completely empty. The astrophysics community did not panic, but it did pay very close attention. Several plausible explanations were offered. The most popular was hierarchical merging. In dense stellar environments like globular clusters, where hundreds of thousands of stars are packed into a relatively small volume, black holes can form, sink to the centre through gravitational interactions, find each other, and merge. The remnant of that merger is a new, larger black hole. If that larger black hole stays in the cluster, it can find another partner and merge again, growing with each generation. Through enough successive mergers, a black hole could in principle build up mass past the pair instability threshold. This explanation was plausible for GW190521. An 85 solar mass black hole could be a second generation object, formed by the merger of 2 smaller black holes each around 40 solar masses. The math worked. The stellar environment made sense. The event was unusual, but it was not inexplicable. But there were cracks in the explanation even then. When 2 non-spinning black holes merge, general relativity predicts the remnant will have a spin of about 0.7. That spin gets added to whatever mass the remnant gains from its next merger. Over multiple generations, the spins should randomize. First-generation black holes formed from stellar collapse tend to have modest spins, between 0 and 0.3 or so. Second-generation objects get spins near 0.7. Third-generation objects can have even higher spins, but the distribution becomes broad and messy. The other issue with hierarchical merging is escape velocity. When two black holes merge, the asymmetric emission of gravitational waves gives the remnant a recoil kick, like a gun recoiling when it fires a bullet. This kick can be anywhere from a few tens to several thousand kilometers per second. If the kick exceeds the escape velocity of the cluster, the merged black hole is ejected into interstellar space and can never merge again. For most globular clusters, the escape velocity is only about 50 kilometers per second. For the most massive nuclear star clusters, it might reach several hundred. Getting a second-generation black hole to stay put long enough to merge again requires either a very low kick, which is unlikely, or a very massive environment, which is rare. GW190521 could be explained within these constraints. Barely. It required favourable assumptions about the environment and the kick velocity, but the scenario was not ruled out. GW23112 made all of these problems worse, much worse. Both component black holes, at roughly 140 and 100 solar masses, were deep inside the mass gap, not at the edge, not in the ambiguous zone where the gap boundaries are debated. Both were well within the range where pair instability supernovae should have destroyed their parent stars completely. And both were spinning at extraordinary rates, with measured spin magnitudes of roughly 0.9 and 0.8 on a scale where 1.0 is the absolute maximum allowed by Einstein's general relativity. Getting a 140 solar mass black hole through hierarchical merging would require at least 3 successive mergers, starting from a black holes around 35 solar masses each, with each generation's remnant successfully avoiding ejection from its environment, successfully finding a new partner, and successfully merging again. The probability of this chain of events occurring is not 0, but it is small, and the resulting spin distribution does not match. Hierarchical mergers produce spins that trend towards 0.7 and then scatter. Getting both components to 0.9 through this channel would require a level of fine-tuning that makes the scenario statistically implausible. There was also the question of alignment. The spins of hierarchically merged black holes tend to be randomly oriented relative to their orbital plane. This is because each successive merger scrambles the spin direction. GW231123 showed hints that the two black holes' spins were not perfectly aligned, which superficially supports a dynamical formation scenario. But the magnitudes of the spins, both near 0.9, remain stubbornly difficult to explain through any known hierarchical pathway. Other explanations were proposed and considered. Perhaps the black holes formed in the accretion disk of an active galactic nucleus, where the extreme densities and gas dynamics could facilitate rapid mergers and growth. Perhaps they were primordial black holes, formed in the first fraction of a second after the Big Bang from density fluctuations in the early universe, objects that would not be subject to the pair instability mass gap because they were never formed from stars. Perhaps the nuclear reaction rates that determine the boundaries of the mass gap were wrong by a larger margin than anyone had assumed, and the gap was narrower or non-existent. Each of these alternatives had problems. Primordial black holes in this mass range face constraints from other observations. Nuclear reaction rate uncertainties could shift the gap boundaries by perhaps 10 to 15 solar masses, not enough to accommodate objects at 100 and 140 solar masses. Formation in AGN disks is plausible but poorly constrained, and no model had demonstrated it could reliably produce the specific mass and spin combination observed. The signal sat in the data for 18 months. The LIGO-Virgo-Cagra collaboration announced the detection publicly on July 14th, 2025, at the International Conference on General Relativity and Gravitation in Glasgow, Scotland. The announcement made headlines, but it came with an unusual caveat from the collaboration itself. Charlie Hoy of the University of Portsmouth, a member of the team, noted that the black holes appear to be spinning very rapidly, near the limit allowed by Einstein's theory of general relativity, and that this makes the signal difficult to model and interpret. The difficulty was not just academic. The signal lasted 1/10 of a second. For typical black hole mergers detected by LIGO, the signal builds up gradually over many orbital cycles. Scientists can use the early, lower frequency part of the signal to measure the masses, and the later, higher frequency part to measure the spins and orbital parameters. The long build-up provides redundancy, like reading a sentence twice to make sure you understood it. For GW2 3111123, there was no build-up. The black holes were so massive that the gravitational wave frequency at which they orbited during the inspiral phase was below LIGO's sensitive frequency band. The detectors only caught the final few cycles in the merger itself. Imagine trying to identify a song from its last note. You can tell something about the instrument and the key, but you miss the melody. The models used to extract physics from gravitational wave signals rely on matching the observed signal against libraries of theoretical waveforms, and those libraries had never been built for objects this extreme. Different waveform families gave slightly different estimates for the masses and spins, and reconciling those differences was, and remains, an ongoing effort. Gregorio Carullo's statement that it would take years to fully unravel this signal was not hyperbole. It was a recognition that the tools of gravitational wave astronomy, which had been developed and refined over 2 decades, were being applied to an event that pushed them past their tested limits. The detection was solid. The physics was clear. 2 forbidden black holes had merged, and the gravitational waves from their collision had travelled across 7 billion light-years of space to arrive at 2 L-shaped detectors in the United States on a Thursday afternoon in November. The data was public. The collaboration had released calibrated data through the Gravitational Wave Open Science Center for anyone to analyse. But after 18 months of analysis, competing hypotheses, and conference presentations that sometimes became arguments, the astrophysics community still did not have a consensus explanation for where these 2 objects had come from. Then in November of 2025, a researcher named Ori Gottlieb published a paper in the astrophysical journal Letters, and the paper's key insight was so simple, so fundamental, that it raised an uncomfortable question about 50 years of prior work. How had everyone missed this? The answer was magnetic fields. Or Gottlieb is an astrophysicist at the Flatiron Institute's Center for Computational Astrophysics in New York City. His paper, published on November 10th, 2025, in the astrophysical journal Letters, carried a title that hinted at its ambition. Spinning into the Gap. The subtitle was more technical. Direct Horizon Collapse as the origin of GW2 31123 from end-to-end general relativistic magnetohydrodynamic simulations. But behind the jargon was a claim that would force astrophysicists to rethink how they model the deaths of the most massive stars in the universe. Gottlieb and his co-authors, Brian Metzger, Danat Issa, Sean Lee, Matteo Renzo and Maximiliano Isi, had done something no one had attempted before. They built a simulation that tracked a massive, low metallicity star through its entire death. Not just the supernova, not just the collapse, everything. From the moment the star began burning helium in its core, through the exhaustion of its fuel, through the collapse, through the formation of a black hole at the centre, and then through what happened next, as the leftover stellar material interacted with the newborn black hole. And crucially, they did all of this while including magnetic fields. That last detail, the inclusion of magnetic fields, was the difference between 50 years of predictions and a single paper that explained the impossible. To understand why magnetic fields matter, and why they had been left out of prior simulations, you need to understand what happens in the seconds after a black hole forms at the centre of a dying star. When a massive star's core collapses and a black hole appears, the story is not over. The outer layers of the star are still falling inward. There is a tremendous amount of material, tens of solar masses worth, that has not yet reached the black hole. In earlier simulations, and in the simplified models that form the basis of the mass gap prediction, this material was assumed to fall straight into the black hole. It collapses. It falls in. The black hole eats everything. End of story. If that were true, then the mass of the final black hole would be roughly equal to the mass of the collapsing stellar core. A 150 solar mass stellar remnant would produce a 150 solar mass black hole. Since 150 solar masses is above the top end of the mass gap, the black hole would sit outside the forbidden range and the mass gap would remain intact. But Gottlieb's simulation showed that this assumption, the assumption that everything falls straight in, is only valid for non-rotating stars, and real stars rotate. When a star is spinning rapidly, the material falling toward the newborn black hole does not plunge directly in. The angular momentum, the rotational energy carried by the infalling gas, prevents a direct plunge. Instead, the material spirals inward and settles into a flattened, rotating structure surrounding the black hole. This is called an accretion disk. Accretion disks are among the most studied objects in astrophysics. They appear around supermassive black holes in the centers of galaxies, around young stars still forming planets, and in X-ray binary systems where a black hole or neutron star pulls material off a companion star. The physics of accretion disks is well established. What had not been studied in detail was what happens when an accretion disk forms around a newborn black hole inside a collapsing star, in the presence of realistic magnetic fields. The magnetic fields are there because the parent star had them. All stars have magnetic fields, generated by the churning motion of electrically conducting plasma in their interiors, a process called dynamo action. When the star collapses, those magnetic fields get compressed and amplified. Additionally, the swirling motion of the accretion disk itself can amplify magnetic fields through a mechanism called the magnetorotational instability. The result is that the accretion disk around a newborn black hole is threaded with magnetic field lines that grow stronger as the collapse proceeds. These amplified magnetic fields do something dramatic. They launch outflows. The magnetic field lines thread through the rotating disk and through the spinning black hole itself. The rotation of the black hole twists the field lines, winding them up like spaghetti around a fork. The twisted, tightly wound magnetic fields act like a spring. They generate enormous pressure along the rotational axis of the black hole, driving material outward in two narrow jets, one from each pole. These jets can reach velocities approaching the speed of light. The jets carry material away from the black hole. Material that would otherwise have fallen in and added to the black hole's mass is instead flung outward into space. And the jets do not just carry mass, they carry angular momentum. The magnetic fields act as a brake on the black hole's rotation, extracting spin energy and converting it into the kinetic energy of the outflows. This is the mechanism, and its consequences are enormous. If the magnetic fields in the collapsing star are strong, the jets are immense. They launch early in the collapse, before much material has had time to fall into the black hole. A large fraction of the stellar material is ejected. The final black hole ends up much lighter than the collapsing star. And because the magnetic fields have extracted angular momentum, the black hole spins more slowly. If the magnetic fields are weak, the jets are feeble or non-existent. Almost all of the stellar material falls into the black hole. The final black hole is nearly as massive as the collapsing core, and it spins rapidly because the infalling material has transferred its angular momentum to the black hole without anything to slow it down. This creates a relationship between mass and spin that is not a coincidence or a fine-tuned outcome. It is a natural physical consequence of magnetic field strength. Strong fields produce lighter, slower spinning black holes. Weak fields produce heavier, faster spinning black holes. And in the moderate range you get objects that land squarely inside the mass gap, with spins near but not at the maximum. Gottlieb's team simulated multiple scenarios, varying the initial magnetic field strength from very strong to moderate to weak. In every case, the star they started with was 250 solar masses, low metallicity, meaning it contained very few elements heavier than hydrogen and helium. This is the kind of star that would have been common in the early universe, when the first generations of stars formed from nearly pristine hydrogen and helium gas. Over its lifetime, this star burned through a significant fraction of its mass. By the time it reached the end of its fuel, it had slimmed down to roughly 150 solar masses. At 150 solar masses, the helium core was above the upper boundary of the pair instability range, meaning the star could collapse into a black hole without being completely destroyed. This is a critical detail. The star sidestepped the pair instability mechanism not because the mechanism does not work, but because the star was massive enough to collapse before pair production could fully develop. In the simulation without magnetic fields, or with negligible fields, the collapse proceeded as prior models had predicted. The stellar material fell into the black hole. The final black hole had a mass close to 150 solar masses, sitting just above the mass gap. No surprise. But when realistic magnetic fields were included, the outcome changed dramatically. In the case with moderate magnetic fields, the accretion disk formed as expected. Magnetic fields amplified through disk instabilities. Jets eventually launched, but only after a significant fraction of the stellar material had already been accreted. The jets removed some mass and angular momentum, but not enough to prevent the formation of a heavy, rapidly spinning black hole. The final mass ended up in the 90 to 120 solar mass range, with a spin near 0.9, inside the mass gap. In the case with strong magnetic fields, the jets launched early, punching through the collapsing stellar envelope in a fraction of a second. They ejected up to half the star's remaining mass. The final black hole was lighter still, perhaps 70 to 90 solar masses, and spun more slowly, also inside the mass gap. In the case with very strong magnetic fields, the jets were so intense that they stripped away most of the infalling material. The black hole barely grew beyond its initial formation mass. It ended up near the lower boundary of the mass gap, spinning relatively slowly. The key result was that by varying the magnetic field strength across a physically reasonable range, the simulation could produce black holes spanning the entire mass gap from its lower edge to its upper edge, with spins ranging from moderate to near maximum. And the specific combination of mass and spin for objects produced with moderate magnetic fields match the observed properties of the two black holes in GW231123 almost exactly. Gottlieb stated the finding plainly. No one has considered these systems the way we did. Previously, astronomers just took a shortcut and neglected the magnetic fields. But once you consider magnetic fields, you can actually explain the origins of this unique event. The word shortcut is important. It is not an accusation. The simulations required to include magnetic fields in a self-consistent way during stellar collapse are computationally extraordinary. They require solving the equations of general relativity, fluid dynamics, and electromagnetism simultaneously in 3 dimensions, at resolutions fine enough to capture both the black hole's event horizon, which is a few kilometers across, and the expanding jets, which extend for hundreds of thousands of kilometers. These are called GRM-HD simulations, General Relativistic Magnetohydrodynamic, and running them requires supercomputers and months of computation time. Previous researchers had not neglected magnetic fields out of laziness. They had neglected them because including them was, until recently, computationally impossible. The tools to perform these simulations at the necessary fidelity simply did not exist 10 years ago. Gottlieb's team benefited from advances in computational methods, hardware capabilities, and adaptive mesh refinement techniques that allowed them to resolve the jet launching region near the black hole while simultaneously tracking the global structure of the collapsing star. The result also produced a testable prediction. When a massive star collapses in this way, and magnetic fields eject a large fraction of the stellar material in relativistic jets, the energy of those jets should be observable. Specifically, the jets would produce extremely energetic gamma-ray bursts, transient flashes of gamma radiation that last anywhere from a fraction of a second to several minutes. These gamma-ray bursts would be among the most luminous events in the universe, potentially comparable to the brightest bursts ever detected. This means the formation of mass-gap black holes through magnetic ejection is not purely a theoretical prediction. It comes with an observational signature. If this mechanism operates, there should be gamma-ray bursts associated with the formation of these objects, particularly in the high redshift universe, where low metallicity stars were common. Existing gamma-ray telescopes may already have data that could confirm or refute this prediction. The paper also noted that the mechanism is consistent with GW190521, the 2020 event that first hinted at mass-gap black holes. The magnetic ejection pathway could produce black holes with the masses and spins inferred for GW190521 as well, suggesting that this is not a one-off explanation tailored to a single event, but a general formation channel that may populate the mass gap across a range of masses and environments. There is something worth pausing on here. For more than 50 years, the pair instability mass gap was treated as a firm prediction of stellar evolution theory. It appeared in textbooks. It guided the design of observational programs. It was used as a benchmark for testing black hole formation models. And it was wrong. Not because the physics of pair instability supernovae was wrong. The physics is correct. Stars in the critical mass range really do destroy themselves. The gap was wrong because the models that predicted it were incomplete. They left out an ingredient that changes the outcome. Magnetic fields are not exotic. They are not speculative. They are ubiquitous in astrophysics. Every star has them. Every accretion disk amplifies them. The role of magnetic fields in launching jets has been studied for decades in the context of active galactic nuclei and gamma-ray bursts. What had not been done was connecting that well-understood jet physics to the specific problem of black hole formation during stellar collapse. The gap is not empty because pair instability supernovae cannot destroy stars. It is empty in the simple models because those models assume that all the material from a collapsing star falls directly into the black hole. What you allow for rotation and magnetic fields, which real stars have, the material does not all fall in, some of it gets blown away. And the black hole that forms is lighter than the star that created it, light enough to land inside the range that was supposed to be forbidden. Gottlieb also identified an additional consequence of the magnetic ejection process. The jets can impart a recoil kick to the black hole, similar to the gravitational wave recoil from mergers, but arising from a different mechanism. This kick can shift the black hole's velocity relative to its birth environment, and importantly, can tilt the black hole's spin axis relative to the orbital plane if it later pairs up with another black hole for a merger. This could explain the hints of spin-orbit misalignment seen in GW2 31123 signal. The paper was published, the data was shared, the simulations were reproducible. And for the first time, the forbidden black holes had a plausible origin story that did not require exotic new physics, did not require fine-tuned hierarchical merging, and did not require abandoning the pair instability mechanism. The gap still exists in the sense that pair instability supernovae still destroy stars, but it is not empty, because the black holes that end up inside it were born from stars massive enough to avoid pair instability, and then lost mass through magnetically driven jets after the black hole formed. The forbidden zone was never truly forbidden. It was just hidden behind an assumption that nobody had checked. But solving the mystery of where these black holes came from opened a different kind of question. When the two forbidden black holes merged and became a single 225 solar mass object, that new black hole did not just sit there quietly. It vibrated, it rang, and the sound it made, encoded in gravitational waves, carried information about the nature of gravity itself. That sound, when scientists analysed it, did not behave the way anyone expected. When two black holes merge, the event does not end at the moment they combine. What follows is one of the strangest phenomena in physics, and it may ultimately be more important than the merger itself. In the fraction of a second after two black holes become one, the newly formed object is not yet a proper black hole. It is a distorted, asymmetric, violently wobbling mass of warped space-time. The shape of its event horizon is lumpy and irregular, bulging in some places and pinched in others like a water balloon that has just been squeezed. Over the next few milliseconds, this distortion smooths out. The black hole radiates away its imperfections as gravitational waves, shedding energy in the form of ripples in space-time until it settles into a perfectly symmetric, stable rotating shape. This process is called ring-down, and it is exactly what the name suggests. The black hole rings like a bell. Just as a bell vibrates at specific frequencies determined by its size, shape and material, a black hole vibrates at specific frequencies determined by its mass and spin. These frequencies are called quasi-normal modes. They are quasi-normal because, unlike a perfect bell that rings forever in the absence of friction, a black hole's vibrations are damped. Each mode has a frequency at which it oscillates and a decay time over which it fades. Together, these two properties, the frequency and the damping time, encode the mass and spin of the black hole. This is an extraordinary fact, and it comes directly from a mathematical result proven in the 1960s by a New Zealand mathematician named Roy Kerr. Kerr solved Einstein's field equations of general relativity for the case of a rotating black hole and found that the solution is completely described by just two numbers: mass and spin. Nothing else. A rotating black hole has no other properties. It has no composition. It has no internal structure that can be probed. It has no memory of what fell into it to create it. Two black holes with the same mass and same spin are identical in every measurable way, regardless of whether one was formed from a collapsing star and the other from a merger of two neutron stars. This is called the no-hair theorem. A black hole has no hair, meaning no distinguishing features beyond mass, spin, and electrical charge, and in practice the charge is always negligible for astrophysical black holes. Every black hole in the universe, from the 5 solar mass remnants of ordinary stellar collapse to the 4 million solar mass behemoth at the centre of our own galaxy, is described by the same Kerr solution. If this is true, then the ring-down frequencies of a black hole tell you everything there is to know about it, and if you can measure multiple ring-down frequencies from the same event, you can test whether the object is actually a Kerr black hole as general relativity demands. This is called black hole spectroscopy, and it is one of the most ambitious goals in gravitational wave astronomy. Think of it like identifying a musical instrument by its sound. If you strike a piano key, it produces a fundamental frequency and a series of overtones, higher-pitched harmonics that give the piano its characteristic sound. If you record those frequencies and compare them against a database of known instruments, you can identify not just that it is a piano, but what size and what tuning. Black hole spectroscopy works the same way. The quasi-normal modes are the frequencies, the mass and spin are the instrument. If you detect multiple modes and they all point to the same mass and spin, you have confirmed that the object is a Kerr black hole. If the modes are inconsistent, you have found evidence that the object is something else, something general relativity does not predict, and the implications for fundamental physics would be difficult to overstate. For GW2 31123, the ring-down was analysed by researchers at the Flatiron Institute and by independent teams around the world. The results were intriguing and in some ways unsettling. The merged black hole at 225 solar masses, was the most massive object whose ring-down had ever been measured by LEGO. Its vibrations were loud enough to detect multiple quasi-normal modes. Will Farr, a researcher at the Centre for Computational Astrophysics who was involved in the analysis, described the results carefully. Each remnant black hole emits waves as discrete tones during the ring-down phase. The combination of tones can in principle be used to characterize the properties of the space-time near the black hole. For GRDW2 311123, at least 2 separate tones were detected, but the pattern of those tones did not correspond straightforwardly to what researchers expected for such a system. A separate analysis, published as a preprint in September 2025, went further. The researchers detected a specific higher harmonic quasi-normal mode, designated the 2-0-0 mode, an axis-symmetric vibration that represents the black hole oscillating in a pumpkin-like deformation, rather than the more common football-like deformation. The statistical confidence was extremely high, with a Bayes factor indicating overwhelming evidence for the mode's presence. What was unusual about this detection is that the axis-symmetric mode was the dominant component. In a typical binary merger, where 2 black holes spiral around each other in a gradually tightening orbit before coalescing, the dominant ring-down mode is the so-called 2-2-0 mode, a quadrupolar oscillation that produces a distinct gravitational wave pattern. The dominance of the 2-0-0 mode suggested something different about the merger geometry. One possible explanation is that the 2 black holes collided in a nearly head-on trajectory, rather than a standard in spiral. A head-on collision would excite the axis-symmetric mode more efficiently than the quadrupolar mode, producing exactly the ring-down pattern that was observed. The analysis also confirmed that the inferred remnant properties, mass and spin, were consistent with the predictions of the no-hair theorem. The modes pointed to a Kerr black hole. General relativity was not violated, but the unusual mode structure raised questions about the dynamics of the merger itself. How did 2 such massive, rapidly spinning black holes end up on a nearly head-on trajectory? Standard binary evolution, where 2 stars orbit each other and both collapse into black holes, produces roughly circular in spirals, not head-on collisions. Dynamical encounters in dense stellar environments can produce more eccentric orbits, but a truly head-on collision is rare even in the densest clusters. This is one of those situations where answering one question creates 3 new ones. The magnetic field mechanism explained where the black holes came from. The ring-down analysis confirmed that the merge product was a legitimate black hole, as Einstein described. But the mode pattern suggested the collision itself was unusual, perhaps pointing to a formation environment or dynamical history that no current model fully captures. To put the ring-down of GW2 31123 into context, it helps to look at what happened 2 years later, on January 14th, 2025. On that date, LIGO recorded a gravitational wave signal designated GW2 50114. By any measure, it was the clearest black hole merger signal ever detected. The signal-to-noise ratio, a measure of how loudly the signal stands above the detector's background noise, was higher than any previous event. The reason was a combination of improvements in detector sensitivity that LIGO had implemented between observing runs and the favourable properties of the merger itself, including moderate masses that placed the signal squarely in LIGO's most sensitive frequency range and a relatively close distance. GW2 50114 became a benchmark event for testing general relativity. With such a clear signal, researchers could apply the most demanding test ever performed on a black hole merger. They detected for the first time with high confidence 2 distinct ring-down modes in the data. The fundamental quadrupolar mode in its first overtone, oscillating at slightly different frequencies and decaying at different rates. Both modes pointed to the same mass and spin for the remnant black hole exactly as the Kerr solution demands. They match perfectly. The analysis also confirmed Stephen Hawking's area theorem, a prediction from 1971 that states the surface area of a black hole's event horizon can never decrease. When two black holes merge, the area of the final event horizon must be at least as large as the sum of the areas of the two original black holes. Using the masses and spins extracted from GW2 50114, the researchers showed that the area did indeed increase, providing the most direct observational confirmation of Hawking's prediction to date. GW2 50114 was a triumph for general relativity. Every test passed, every prediction confirmed. The merged black hole rang at precisely the frequencies Einstein's equations demanded. But here is where the contrast with GW2 31123 becomes important. GW2 50114 involved relatively ordinary black holes. Its component masses were well below the mass gap. Its spins were moderate. The merger dynamics were standard. It was, in a sense, a clean experiment, a test of general relativity under conditions where the theory was expected to work, and where the theoretical models used to interpret the signal were well validated. GW2 31123 was none of those things. Its masses were in the forbidden range. Its spins were near maximum. The signal lasted only 1/10 of a second. The waveform models used to interpret the data gave slightly different answers depending on which model was used. The ring-down modes were unusual. The merger geometry may have been non-standard. If there is a regime where general relativity might deviate from its predictions, if there is a condition under which Einstein's century-old theory might begin to crack, it would be in exactly this kind of event. Two of the most massive fastest-spinning black holes ever observed, colliding in what may have been a nearly head-on trajectory, producing a remnant that vibrated in a pattern no one had predicted. General relativity passed the test of GW2 31123. The observed ring-down modes, while unusual in their relative strengths, were consistent with the Kerr solution. But consistent is not the same as precisely verified. The precision of the GW2 31123 measurement was lower than that of GW2 50114 because the signal was shorter, noisier relative to its complexity, and harder to model. The test was less conclusive. This does not mean relativity failed. It means the test was operating at the limit of Courant capability, and the next event of this type, observed with a more sensitive detector, could either confirm Einstein's equations with greater precision, or reveal the first hint that they break down under the most extreme conditions, or as Gottlieb himself acknowledged this tension. Extreme events like W23112 free-stretch general relativity to its breaking point. The word stretch is precise. The theory held, but it was stretched further than it had ever been stretched before, and for a theory that has passed every test thrown at it for 110 years, the fact that this event even approached the limits of what can be tested is itself significant. There is a deeper question here that goes beyond the specific physics. When you listen to a black hole ring, you are listening to the shape of space-time itself. The frequencies encode the geometry. If the geometry matches what Einstein predicted, you have confirmed that space-time near a black hole behaves as a smooth curved surface, described by general relativity. If it does not match, you have discovered something new. Perhaps black holes have internal structure that the no-hair theorem does not account for. Perhaps quantum gravity effects, which should in principle become important near the singularity at a black hole's centre, leak outward and affect the ring down in measurable ways. Perhaps general relativity is simply not the complete description of gravity that it appears to be. None of these possibilities have been confirmed. But each one is the kind of discovery that would reshape our understanding of the universe at its most fundamental level, and each one becomes testable as gravitational wave detectors improve and as events like GW2 31123 are observed with greater clarity. For now, Einstein survives, the Kerr solution survives, the no-hair theorem survives, but the fact that a collision between two forbidden black holes, objects that were not supposed to exist, produced ring-down tones that did not match the expected pattern, even while remaining broadly consistent with general relativity, suggests that the universe is operating in a regime that our models have barely explored. The gravitational wave signal from GW 231123 travelled for 7 billion years to reach us. It passed through expanding space, through galaxy clusters and voids, through regions of the universe that did not exist when the collision happened. When those waves were generated, the universe was roughly half its current age. The stars that would become our sun had not yet been born. The Milky Way was smaller, younger, still assembling itself through mergers with dwarf galaxies. That collision happened in a universe that looked very different from the one we see today, and the magnetic field mechanism that created those forbidden black holes has its deepest implications, not in the present-day cosmos, but in the even more distant past. In the first billion years after the Big Bang, when the first stars were born and the first black holes formed from their deaths, because those first stars were exactly the kind of stars that Gottlieb's mechanism applies to. Massive, rapidly rotating, low metallicity, threaded with magnetic fields, and if this process operated at scale in the early universe, it would have seeded space with far more massive black holes than any previous model predicted, changing the story of how the universe grew from a smooth, hot plasma into the structured cosmos of galaxies, clusters and supermassive black holes that we observe today. The collision that produced GW 231123 happened roughly 7 billion years ago. That means it occurred when the universe was approximately half its current age, about 6 to 7 billion years after the Big Bang. By that point in cosmic history, galaxies had already formed, stars had been burning for billions of years. The chemical elements that would eventually make up rocky planets like Earth had already been forged in the interiors of earlier stellar generations and scattered into the interstellar medium by supernovae. But Gottlieb's magnetic field mechanism does not just explain a single event in the middle of cosmic history. Its implications reach much further back, to the very beginning. The first stars in the universe were nothing like the stars we see today. They formed roughly 100 to 200 million years after the Big Bang, in a cosmos that contained almost nothing except hydrogen, helium, and trace amounts of lithium. There was no carbon, no oxygen, no iron, no silicon. The interstellar medium was chemically pristine, composed entirely of the elements produced in the first few minutes after the Big Bang in a process called Big Bang nucleosynthesis. This matters because the absence of heavy elements changes how stars form and how massive they can grow. In the modern universe, heavy elements, collectively called metals, by astronomers regardless of whether they are actually metallic, play a critical role in cooling gas clouds during star formation. When a gas cloud collapses under gravity, it heats up. If the gas contains carbon, oxygen, and other heavy elements, those atoms radiate energy efficiently, allowing the cloud to cool, fragment and form relatively small, modest stars like our Sun. Without those coolants, the gas stays hot, the pressure remains high, and the collapsing cloud does not fragment as easily. The result is fewer, more massive stars. The first generation of stars, called Population 3 stars, are predicted to have been enormous. Theoretical models place their masses anywhere from tens to hundreds of solar masses, with some estimates suggesting individual stars could have reached 300 or even 1,000 solar masses. No Population 3 star has ever been directly observed. They burned hot and bright and died quickly, within a few million years, long before the light from their era could be captured by any telescope that exists today. But their deaths shaped everything that followed. When a Population 3 star dies, it follows the same physics that governs stellar death in the modern universe. If it is in the pair instability mass range, it destroys itself completely. If it is above that range, it collapses directly into a black hole. And if the magnetic field mechanism that Gottlieb described was operative in these early stars, and there is no physical reason it would not be, since these stars rotated and had magnetic fields just like modern stars. Then the mass gap would have been populated with black holes from the very first generation of stellar deaths. This is where the implications become genuinely significant. One of the most persistent puzzles in modern astronomy is the existence of supermassive black holes in the very early universe. These are black holes weighing millions to billions of solar masses, sitting at the centres of quasars, which are galaxies with incredibly bright cores powered by material falling into the central black hole at prodigious rates. The light from these quasars tells us their masses and distances, and some of them are astonishingly old. The James Webb Space Telescope, launched in December 2021 and operational since mid-2022, has been observing the distant universe in infrared light, peering back to times when the universe was less than 1 billion years old. Among its discoveries are quasars and active galactic nuclei powered by black holes weighing hundreds of millions to over 1 billion solar masses, existing when the universe was only 600 to 800 million years old. Earlier surveys with the Sloan Digital Sky Survey and other ground-based telescopes had already found quasars at similar distances, but Webb has expanded the sample and pushed the observations to even earlier cosmic times. The problem is straightforward. How do you grow a black hole from stellar mass, say 50 or 100 solar masses, to 1 billion solar masses in less than 700 million years? The standard mechanism for black hole growth is accretion, the process by which a black hole pulls in surrounding gas, which spirals inward through an accretion disk, heats up, radiates energy, and eventually falls past the event horizon. Accretion can grow a black hole, but it has a speed limit. That speed limit is called the Eddington limit, named after the British astrophysicist Arthur Eddington, who derived it in 1926. The Eddington limit is the maximum rate at which a black hole can accrete material while remaining stable. At higher accretion rates, the radiation pressure from the hot infalling gas pushes outward so strongly that it blows the gas away, shutting off the accretion. The Eddington limit depends on the mass of the black hole, and it turns out that at this maximum rate, a black hole doubles its mass roughly every 45 million years. Start with a 100 solar mass seed black hole, accreting at the Eddington limit continuously, and after 700 million years you get a black hole of roughly 10 million solar masses. That is a lot, but it's not 1 billion. To reach 1 billion solar masses in 700 million years requires either a much more massive seed or a mechanism to exceed the Eddington limit, or both, and both options have problems. Exceeding the Eddington limit is called super Eddington accretion, and it is possible in certain conditions, particularly when the accretion flow is so thick that the radiation gets trapped and cannot escape to push the gas away. But sustaining super Eddington accretion for hundreds of millions of years requires a constant dense supply of gas, which is not guaranteed in the early universe. The alternative is to start with a bigger seed. If your initial black hole is not 100 solar masses, but 10,000 or 100,000 solar masses, the Eddington limit still applies, but you have a massive head start. These heavy seeds could form through direct collapse of massive gas clouds in the early universe, a mechanism called direct collapse black holes. But forming a 100,000 solar mass black hole directly from a gas cloud requires very specific conditions, including the absence of molecular hydrogen coolants and the presence of a strong ultraviolet radiation field to prevent the gas from fragmenting. These conditions may have been rare. This is where Yajudo W2, 311123 and the magnetic field mechanism enter the picture. If Gottlieb's process operated widely among population 3 stars, it would have produced a population of black holes in the 60 to 130 solar mass range from the very first generation of stellar deaths. These are heavier than the standard black hole, seeds produced by ordinary stellar collapse, which typically cap out around 40 to 60 solar masses. More massive seeds means faster growth. A 130 solar mass seed accreting at the Eddington limit reaches a billion solar masses, roughly 150 million years sooner than a 50 solar mass seed. In the tight timeline of the early universe, where every 100 million years counts, that head start could be the difference between explaining the observed quasar population and not. Additionally, these mass-gap black holes could grow through mergers with other black holes. In the dense environments of the early universe, where proto-galaxies were assembling through mergers of smaller structures, encounters between black holes would have been more frequent than they are today. If mass-gap black holes merged with each other, they could rapidly build up to intermediate mass scales, a few hundred to a few thousand solar masses, providing even more massive seeds for subsequent accretion-driven growth. The term intermediate mass black hole refers to objects in the range of roughly 100 to 100,000 solar masses. These have been predicted for decades but have proven stubbornly difficult to confirm observationally. We know stellar mass black holes exist because we see them in X-ray binaries and gravitational wave mergers. We know supermassive black holes exist because we observe their effects at the centres of virtually every large galaxy. But the bridge between these two populations, the intermediate mass range, has been largely empty. GW2 31123's remnant at 225 solar masses is an intermediate mass black hole. It is in fact one of the most convincing intermediate mass black hole candidates ever detected, because its mass is directly measured from the gravitational wave signal rather than inferred from indirect observational proxies. If the magnetic field formation pathway produces these objects routinely, and if they can merge repeatedly in dense environments, then the intermediate mass range may be much more densely populated than current catalogues suggest. The gap between stellar mass and supermassive black holes may not be a gap at all, but a bridge that we have only just begun to cross. There is another angle to this that is worth exploring. The connection between GW2, 31123 and the early universe is not just about seeds, it is about feedback. When a massive black hole forms through Gottlieb's mechanism and launches fast-moving relativistic jets during the collapse, those jets carry enormous energy into the surrounding interstellar medium. They heat gas, compress nearby clouds, and influence the formation of subsequent generations of stars. In the early universe, this kind of feedback could have had outsized effects on the evolution of the first galaxies. Modern galaxies are shaped by feedback from supermassive black holes at their centres. When material falls into a supermassive black hole, the energy released can drive outflows that sweep gas out of the galaxy entirely, shutting off star formation and regulating the galaxy's growth. This process, called AGN feedback, is one of the key ingredients in models of galaxy evolution. If mass-gap black holes in the early universe were producing high-energy jets during their formation, they may have contributed a form of early universe feedback that current galaxy formation models do not include. This is speculative. Nobody has confirmed that population 3 stars form mass-gap black holes through magnetic ejection, and no early universe jet associated with this mechanism has been identified. But the physics is sound, the mechanism is general, and the conditions in the early universe, massive low metallicity stars with rapid rotation and magnetic fields, are precisely the conditions under which Gottlieb's simulations predict the mechanism operates most efficiently. The connection runs even deeper when you consider the role of metallicity. Metallicity, the abundance of elements heavier than helium in a star, affects how much mass the star loses through stellar winds during its lifetime. Stars with high metallicity, like those in our galactic neighbourhood today, lose significant mass through radiatively driven winds, which strip away the star's outer layers over millions of years. By the time a high metallicity star reaches the end of its life, it may have lost half or more of its birth mass. Low metallicity stars lose much less mass to winds. They retain more of their original mass throughout their lives, arriving at the moment of collapse much heavier than their high metallicity counterparts. This means that in the early universe, where metallicity was nearly zero, The most massive stars would have been even more massive at the time of collapse than similar stars in the modern universe. A population 3 star born at 250 solar masses might arrive at collapse with 200 solar masses or more, compared to a modern star of the same birth mass that might arrive at collapse with only 100 solar masses after losing half its mass to winds. This makes the magnetic ejection mechanism even more effective in the early universe. Heavier stars at collapse mean more material available for the accretion disk, stronger magnetic fields, more energetic jets, and a wider range of final black hole masses spanning the mass gap. The mechanism does not just work in the early universe, it works better. It works. The LIGO-Virgo-Cagra network has now observed over 300 gravitational wave events since the first detection in 2015. Over 200 of these came during the fourth observing run, which began in May 2023 and is expected to continue into 2025. Each run has brought improvements in detector sensitivity, expanding the volume of space from which mergers can be detected and improving the precision with which masses, spins and distances can be measured. The fifth observing run, expected to begin in late 2026 or early 2027, will push the sensitivity even further. The A+ upgrade to LIGO, which involves improvements to the laser power, mirror coatings, and quantum noise reduction through a technique called frequency-dependent squeezing, is expected to roughly double the detector's range for binary black hole mergers. This means roughly 8 times the volume of space accessible, and correspondingly more events detected per year. Beyond LIGO, the next generation of gravitational wave observatories is already being planned. The Einstein Telescope, a European project, would be built underground in a triangular configuration with arms 10 kilometers long. Cosmic Explorer, an American concept, would extend the LIGO design to arms 40 kilometers long. Both projects aim for sensitivities 10 times greater than current detectors, enabling the detection of black hole mergers across the entire observable universe, including mergers from the epoch when the first stars were dying and the first black holes were forming. In space, the Laser Interferometer Space Antenna, known as LISA, is a European Space Agency mission planned for launch in the 2030s. LISA would deploy 3 spacecraft in a triangular formation, separated by 2.5 million kilometers, forming an interferometer in space that is sensitive to gravitational waves at much lower frequencies than ground-based detectors. At these low frequencies, LISA would detect mergers of supermassive black holes, objects weighing millions of solar masses as they combine during galaxy mergers. This would provide a direct window into the growth of supermassive black holes, the same objects whose origins the magnetic field mechanism may help explain. Each improvement in gravitational wave detection capability opens a new window. The first detection in 2015 proved that binary black holes exist and merge. The next few years of observations established the mass distribution and confirmed that black holes below the mass gap form primarily through stellar collapse. GW190521 in 2020 hinted that the gap might not be empty. GW231123 in 2023 confirmed it. The magnetic field explanation in 2025 showed why. The next frontier is not just detecting more events, it is connecting the gravitational wave observations of individual mergers to the population-level statistics of black holes across cosmic time. How many mass gap black holes are there? How does the rate of mass gap mergers change with redshift, with distance, with cosmic age? Does the magnetic field formation pathway dominate at a high redshift? When stars were more massive and lower in metallicity, do the mergers cluster in certain environments, like globular clusters or nuclear star clusters, or the disks of active galactic nuclei? These are not hypothetical questions. They are the driving science goals of the next decade of gravitational wave astronomy. And every answer traces back in one form or another to the question that EGW231123 forced the community to confront. If the mass gap is not empty, Then what else have we been wrong about? The investigation of GW2 311123 did not end with a resolution. It ended with a list, and the list is longer than anyone expected. If you were to take every unresolved question that this single gravitational wave event has generated and pin them to a wall, you would find yourself looking at something that resembles a caseboard in a detective's office. Red strings connecting seemingly unrelated observations, each question leading to two more, and none of them fully answered. 7 open investigations, all born from 1/10 of a second of data recorded on a Thursday afternoon in November 2023. The first question is whether the pair instability mass gap is real, partially populated, or something else entirely. Before GW2 31123, the gap was treated as a firm prediction. Stars in the critical mass range destroy themselves through pair instability, supernovae, leaving nothing behind. The gap should be empty. But Gottlieb's magnetic field mechanism shows that black holes can be deposited inside the gap through a different pathway, one that does not violate pair instability physics but circumvents it. The stars that produce these black holes are massive enough to avoid pair instability, but they lose mass through magnetically driven jets after the black hole forms, landing the final object inside the forbidden range. This raises a question that the community has not yet settled. Is the gap partially filled with a small population of mass gap black holes produced through the magnetic ejection channel, or is the gap robustly populated to the point where it is not really a gap at all? The answer depends on how common the necessary conditions are: massive stars, low metallicity, rapid rotation and significant magnetic fields. In the early universe, where metallicity was low and stars were massive, these conditions may have been widespread. In the modern universe, where metallicity is higher and the most massive stars lose significant mass to winds before they die, the conditions may be rare. The LIGO data so far shows a clear drop-off in the number of black holes above 50 to 60 solar masses, consistent with a gap that exists but is not completely empty. GW190521 and GW231123 are the two most prominent objects inside the gap, but with over 300 events detected and counting, and with sensitivity improving every year, the statistical picture will sharpen. If the gap is partially filled, the distribution of black hole masses inside it should follow a specific pattern predicted by Gottlieb's mechanism, with a correlation between mass and spin that maps onto the strength of the progenitor's magnetic field. Testing this prediction requires a larger sample of mass gap events, and the 5th observing run may provide it. The second question concerns the mass-spin relationship itself. Gottlieb simulations predict a natural correlation. Heavier mass gap black holes should spin faster, lighter ones should spin slower. This is because stronger magnetic fields extract more mass and more angular momentum, producing lighter and slower spinning remnants, while weaker fields allow the black hole to retain more mass and spin up through accretion. If this correlation holds in the data, if future mass gap detections show a consistent trend between mass and spin, it would provide strong evidence for the magnetic ejection formation channel, and help constrain the distribution of magnetic field strengths in the progenitor stars. So far the sample is too small to test this rigorously. GW2 31123's 2 components at roughly 140 and 100 solar masses, with spins near 0.9 and 0.8 respectively, are broadly consistent with the prediction, but represent only a single data point. GW190521's components at roughly 85 and 66 solar masses with less well-constrained spins are also broadly consistent, but 2 events do not make a trend. 5 or 10 mass gap detections would begin to reveal whether the predicted correlation exists, and 20 or more would allow a statistically meaningful test. The third question is about the ringdown. When the 225 solar mass black hole settled into its final state after the merger, it vibrated at specific frequencies. Researchers detected at least 2 quasi-normal modes, but the pattern was unusual. the axis-symmetric mode was dominant rather than the quadrupolar mode, suggesting a merger geometry that was not a standard circular in spiral. This could indicate a nearly head-on collision, or it could reflect the effects of the extreme spins on the merger dynamics, or it could be an artifact of the difficulty of modelling such an extreme system with current waveform tools. The question is not whether general relativity was violated. The inferred remnant properties are consistent with a Kerr black hole as predicted by Einstein's equations. The question is whether the unusual mode structure is telling us something about the dynamics of the merger that standard models do not fully capture. A nearly head-on collision has different physics from a gradually tightening in spiral. It produces different gravitational wave signatures, different amounts of energy in different modes, and potentially different final spins. If the unusual ring down is indeed due to a head-on collision, it raises a follow-up question. What astrophysical process puts two black holes on a head-on trajectory? Standard binary evolution produces roughly circular orbits. Dynamical encounters in star clusters can produce eccentric orbits, but truly head-on collisions are rare even in the densest environments. Understanding the formation environment of GW231123's progenitor black holes requires understanding not just how they formed, but how they found each other and collided. The fourth question is about the gamma-ray bursts. Gottlieb's magnetic ejection mechanism predicts that the formation of mass-gap black holes should be accompanied by fast-moving relativistic jets, which would produce energetic gamma-ray bursts observable by telescopes. These bursts would be associated with the formation of the black hole, not with the subsequent merger billions of years later. They would have occurred when the progenitor stars collapsed, presumably in the early universe at high redshift, where low metallicity stars were common. No gamma-ray burst has been definitively linked to this mechanism, but gamma-ray burst astronomy has been observing the sky for decades, and the archives contain thousands of detected bursts. Some fraction of these, particularly the very energetic bursts from high redshift, may have been produced by the magnetic ejection process during the formation of mass-gap black holes. Identifying these events in archival data would require comparing the predicted properties of the burst, their energy, duration, spectrum, and redshift distribution against the observed catalogue. This is a non-trivial analysis, but it is feasible with existing data, and it represents the most direct observational test of Gottlieb's mechanism beyond gravitational wave detection. The fifth question concerns the porosity of the mass gap as a concept. For 50 years, the mass gap was treated as a feature of stellar evolution, a direct consequence of how the most massive stars die. Gottlieb's work shows that the gap can be populated by a mechanism that does not violate stellar evolution physics, but adds an additional step, magnetic ejection, to the process. But this raises the question of whether other mechanisms might also populate the gap. If magnetic fields can do it, what about dark matter? What about modified nuclear reaction rates? What about exotic compact objects like boson stars or dark matter clumps that mimic black holes in gravitational wave signals? Some of these alternatives are more speculative than others, but the fact remains that the pair instability mass gap was treated as robust precisely because no known mechanism could populate it. Now one known mechanism can. The gap is no longer a hard boundary. It is a feature of incomplete models, and once you accept that the models were incomplete in one way, it becomes natural to ask whether they might be incomplete in other ways as well. This question will be addressed not just by LIGO, but by the intersection of gravitational wave astronomy with other fields. If mass-gap black holes are produced through stellar collapse with magnetic ejection, they should leave chemical signatures in the interstellar medium from the material ejected by the jets. If they are produced through hierarchical merging in star clusters, the rate and properties of mass-gap mergers should correlate with the distribution and masses of star clusters. If they are produced through some exotic mechanism involving dark matter or new physics, the distribution of mass-gap objects in mass, spin, and redshift should differ from the predictions of standard astrophysics. The sixth question is about the shape of the universe's black hole population. Every gravitational wave detection adds a point to the map of black hole masses and spins. Over time, this map reveals the underlying distribution, the demographics of the black hole population. Before GW231123, the mass distribution showed a clear peak around 8 to 10 solar masses, a secondary peak around 35 solar masses, and a sharp drop-off above 50. The mass gap appeared as a valley in the landscape. With GW231123 and the magnetic ejection mechanism, the landscape may need to be redrawn. If mass gap black holes are produced at a significant rate in the early universe, the population at high redshift may look very different from the population at low redshift. Stars were more massive and lower in metallicity in the past, meaning the magnetic ejection mechanism was more efficient and more common. The black hole mass function may evolve with cosmic time, with the mass gap being more populated in the early universe and more empty in the modern era. This evolution would have profound implications for our understanding of galaxy formation and the growth of supermassive black holes. The intermediate mass black holes produced by mass gap mergers could serve as the seeds for supermassive black hole growth. The jets produced during black hole formation could influence early galaxy evolution through feedback. The mergers themselves, releasing enormous amounts of gravitational wave energy, could in principle affect the dynamics of the dense stellar environments where they occur. Mapping the black hole mass function across cosmic time is one of the primary science goals of next-generation gravitational wave detectors. The Einstein Telescope and Cosmic Explorer, with their tenfold improvement in sensitivity, will detect black hole mergers from the epoch of the first stars, directly observing whether the mass gap was populated when the universe was young. LISA, in space, will detect supermassive black hole mergers and measure the masses and spins of the most massive black holes in the universe, connecting the intermediate mass objects produced by stellar collapse to the billion solar mass behemoths at the centres of galaxies. The seventh question is perhaps the most fundamental, and it has nothing to do with black holes specifically. When researchers added up every known source of information about GW231123, the masses, the spins, the ring-down modes, the distance, the inferred formation mechanism, they found that the event pushed multiple frontiers simultaneously. The masses pushed the limits of stellar evolution models. The spins pushed the limits of merger dynamics models. The ring down pushed the limits of waveform models. The formation mechanism pushed the limits of computational astrophysics. And the signal itself pushed the limits of LIGO's detection and analysis capabilities. None of these limits were broken, but all of them were approached. And the question this raises is uncomfortable. How many events like GW231123 have we already missed? LIGO detects gravitational waves above a certain amplitude threshold. Events that are too far away, too low in mass, or too brief to produce a detectable signal are invisible. The network has been operational, off and on, since 2015, but its sensitivity has improved dramatically with each observing run. Events that would have been undetectable in the first run might be detected routinely in the fifth. What this means is that the catalogue of observed events is not a complete census. It is a biased sample, weighted toward the loudest, closest, most favourable events. The true population of merging black holes in the universe is much larger than what LIGO has detected. If mass gap black holes are produced through the magnetic ejection mechanism at a significant rate in the early universe, and if they merge at rates comparable to the rates of subgap mergers, then many of these events are happening right now, producing gravitational waves that are passing through us this very moment, too faint or at too low a frequency for current detectors to pick up. Each improvement in sensitivity opens a new window and reveals events that were previously hidden. The detection of GW231123 was not a fluke. It was the loudest signal from a population that is probably much larger, and the properties of that population, its size, its mass distribution, its evolution over cosmic time, are exactly what the next generation of detectors is designed to measure. 7 questions, none of them answered, all of them connected, and all of them tracing back to 1/10 of a second of data from a collision between 2 objects that were never supposed to exist. The investigation of GW2 311123 is ultimately a human story, carried out by instruments that humans built and interpreted by minds that humans trained. And the people behind this work are worth knowing, because the way this discovery unfolded reveals as much about how science works as the physics itself. The LIGO detectors were conceived in the 1960s and 1970s, decades before the technology existed to make them work. The idea came from several physicists independently, but the people who turned the concept into reality were Kip Thorne and Rainer Weiss, both theoretical physicists who understood that detecting gravitational waves would require measuring distance changes smaller than the diameter of a proton. Weiss, working at MIT, designed the laser interferometer concept that would become LIGO. Thorne, at Caltech, provided the theoretical framework and helped build the scientific case. A third physicist, Barry Barish, took over the project in the mid-1990s and transformed it from a laboratory experiment into a full-scale observatory with the management structure and engineering rigor needed to actually work. All 3 shared the 2017 Nobel Prize in Physics after the first detection, in 2015, but the project had taken nearly 50 years from conception to that moment. Weiss first sketched the idea in 1972. Construction on the 2 LIGO sites began in 1994. The initial detectors operated from 2002 to 2010 without detecting anything. They were not sensitive enough. The detectors were then shut down for a 5-year upgrade to advanced LIGO, which improved the sensitivity by roughly a factor of 10. On September 14th, 2015, 4 days before advanced LIGO was scheduled to officially begin its first observing run, the detectors picked up gravitational waves from 2 black holes, merging 1.3 billion light-years away. The signal was so clear that the scientists initially suspected it was a test injection, a fake signal deliberately planted to test the analysis pipeline. It was not. That first detection proved 2 things simultaneously: that gravitational waves exist exactly as Einstein predicted, and that binary black holes exist and merge within the age of the universe. Both were suspected, but neither had been confirmed. A single observation answered 2 of the biggest open questions in physics. Since then, the pace of discovery has accelerated. The first observing run detected 3 binary black hole mergers. The second run, with improved sensitivity, detected 8 more, plus the first binary neutron star merger, GW170817, which was also observed by telescopes across the electromagnetic spectrum and confirmed that neutron star mergers produce short gamma-ray bursts and forge heavy elements like gold and platinum. The third run, from 2019 to 2020, detected dozens more events, including GW190521, the first hint of mass gap black holes. The fourth run, beginning in May 2023, has detected over 200 events, including GW231123. The improvement in sensitivity from run to run is not incremental, it is transformative. Each factor of 2 improvement in sensitivity increases the volume of space from which events can be detected by a factor of 8, because volume scales as the cube of distance. The fourth observing run, with its improved sensitivity, can detect black hole mergers roughly twice as far away as the second run could, which means it surveys roughly 8 times as much of the universe. This is why the number of detections has exploded. It is not that mergers are happening more frequently, it is that we can now hear them from much farther away. The engineers who maintain these instruments work at a level of precision that borders on the absurd. The mirrors in LIGO weigh 40 kilograms each and hang from glass fibers thinner than a human hair, inside vacuum chambers that maintain a pressure 1/trillionth of atmospheric pressure, lower than the vacuum of outer space. The laser beams travel the 4-kilometre length of each arm 300 times per second, bouncing between the mirrors before recombining at the detector's output. The interference pattern of the recombined beams is sensitive to changes in the arm length of 1/10,000th the diameter of a proton. To achieve this sensitivity, the instruments must be isolated from every possible source of disturbance. Seismic vibrations from traffic, ocean waves, wind, and even the gravitational attraction of passing clouds can mask or mimic a gravitational wave signal. The isolation systems use multiple stages of pendulums, active feedback loops, and vibration damping to hold the mirror steady to within the required precision. The quantum nature of light itself introduces noise, called shot noise, because the laser beam is made of individual photons that arrive at slightly random times. To reduce this, LEGO uses a technique called squeezed light, which manipulates the quantum state of the laser beam to reduce uncertainty in the measurement direction, at the cost of increasing uncertainty in a direction that does not affect the measurement. It sounds like science fiction, but it works, and it has been standard practice since the third observing run. The people who analyse the data are spread across more than 1,600 institutions in over 40 countries, collaborating under the banner of the LEGO Scientific Collaboration, the Virgo Collaboration, and the Kagra Collaboration. When a gravitational wave signal arrives, it is detected by automated search algorithms running in real time, and alerts are sent to the collaboration within minutes. For binary neutron star mergers and neutron star black hole mergers, where electromagnetic counterparts might be visible, these alerts are forwarded to telescope networks around the world so they can point at the source location and look for light. For binary black hole mergers, there is usually no light to see, but the gravitational wave data is rich enough to extract detailed physics. The analysis of GW 31123 was led by teams at multiple institutions, with significant contributions from the Flatiron Institute's Centre for Computational Astrophysics, Cardiff University, the University of Birmingham, the University of Portsmouth and Caltech, among many others. The LEGO Virgo Kagra collaboration operates on a principle of collective authorship, with papers typically listing hundreds or thousands of authors, reflecting the distributed nature of the work. Ore Gottlieb, whose simulation explained the formation of the forbidden black holes, is a relatively young astrophysicist at the Flatiron Institute. His work combined expertise in general relativistic simulations, magnetohydrodynamics and jet physics, fields that are typically studied in separate communities. The insight that magnetic fields could change the mass of a black hole formed during stellar collapse required bridging these communities, applying tools developed for one problem to a different problem that nobody had thought to connect them to. His co-author Brian Metzger is known for predicting the electromagnetic signals from neutron star mergers before they were observed, work that was dramatically confirmed by the detection of GW 170817 in 2017. Maximiliano Isi, another co-author, is an expert in testing general relativity with gravitational waves and was involved in the ring-down analysis of both GW2 31123 and GW2 50114. The team's interdisciplinary expertise was essential because the problem they were solving sat at the intersection of stellar evolution, black hole physics, magnetohydrodynamics, and gravitational wave astronomy. No single specialist could have solved it alone. This is how science works at the frontier. The questions are too complex for any one person or any one field. The answers come from combining tools and perspectives in new ways. From a jet physicist asking what would happen if you included magnetic fields in a stellar collapse simulation. From a gravitational wave analyst asking why the ring-down modes did not match the expected pattern. From an engineer asking whether the quantum noise in the laser could be reduced by another factor of 2. Each contribution is small individually. Together, they move the understanding of the universe forward in a measurable way. The instruments themselves are evolving. The A+ upgrade to LIGO is being implemented between observing runs, improving the sensitivity of the existing detectors through better mirror coatings, increased laser power, and more advanced quantum noise reduction. The 5th observing run, expected to begin in late 2026 or early 2027, will use these improvements to extend the detection range and increase the event rate. Beyond A+, entirely new observatories are being planned. The Einstein Telescope is a European project that would place a gravitational wave detector underground, in a triangular configuration with 3 pairs of arms, each 10 kilometers long. The underground location shields the detector from surface seismic noise, and the triangular design allows it to measure the polarization of gravitational waves, providing additional information about the source. The Einstein Telescope would be sensitive enough to detect black hole mergers from the edge of the observable universe, including mergers from the first billion years after the Big Bang, when the first stars were dying and the first black holes were forming. Cosmic Explorer is an American concept that takes a different approach. Rather than going underground, it would build surface detectors with arms 40 kilometers long, roughly 10 times the length of current LIGO arms. The increased arm length directly improves sensitivity to gravitational waves, and the resulting detector would be able to observe virtually every binary, black hole, merger in the observable universe above a certain mass threshold. With such a detector, events like GW2 31123 would be routine rather than exceptional. The mass gap population would be mapped in detail, and the connection between black hole formation in the early universe and the growth of supermassive black holes could be traced directly. LISA, the Laser Interferometer Space Antenna, operates in a completely different frequency range. Ground-based detectors like LIGO are sensitive to gravitational waves between roughly 10 and several thousand hertz, the frequencies produced by merging stellar mass objects. LISA, with its 2.5 million kilometer arms floating in space, would be sensitive to frequencies between roughly 0.0, 0.001 and 0.1 hertz, the frequencies produced by merging supermassive black holes, compact binary systems in our galaxy, and possibly exotic sources like cosmic strings or phase transitions in the early universe. Together, these future observatories would cover the gravitational wave spectrum from millihertz to kilohertz, spanning the mass range from compact binaries in our own galaxy to billion solar mass mergers at cosmological distances. The picture of the universe that emerges from this multi-frequency gravitational wave astronomy will be fundamentally different from the picture we have today. It will show us how black holes of all sizes form, grow, merge and influence the galaxies around them, and it will tell us eventually whether the pair instability mass gap is really a gap, or whether it is a doorway that we had simply not known how to open. There is one more aspect of our GW2 31123 that is worth sitting with because it speaks to something larger than the physics. The collision happened roughly 7 billion years ago. The gravitational waves left the source and began their journey toward us, travelling at the speed of light through an expanding universe. During those 7 billion years, the waves stretched along with space itself, their frequency shifting lower as the universe grew. They passed through galaxy clusters and cosmic voids, through regions dense with dark matter and regions nearly empty, through the intergalactic medium that fills the vast distances between galaxies. During those 7 billion years, our solar system formed from a collapsing cloud of gas and dust about 4.6 billion years ago. Earth formed, cooled, developed an atmosphere and oceans. Life appeared, evolved, diversified, went through mass extinctions and recoveries. Dinosaurs came and went, mammals rose, primates evolved. Humans appeared, developed language, agriculture, mathematics, physics. And then, roughly a century ago, a physicist named Albert Einstein published a set of equations describing how mass and energy curve the fabric of space and time. Those equations predicted that accelerating masses would produce ripples in space-time that propagate outward at the speed of light. For decades, These ripples were considered too faint to ever detect. The technology did not exist. The sensitivity required was beyond anything engineers could build, but people kept working on it. For 50 years, across multiple generations of scientists and engineers, the technology was developed, refined, tested, improved, and developed again. Mirrors were polished to atomic smoothness. Lasers were stabilized to precisions measured in fractions of wavelengths. Vacuum systems were built that rivaled the emptiness of interstellar space. And on September 14th, 2015, the first gravitational wave signal was detected. 8 years later, on November 23, 2023, those same detectors, improved and refined through 4 successive observing runs, recorded the signal from GW2 31123. Gravitational waves that had been travelling for 7 billion years, launched by a collision between 2 objects that physics say should not exist, arrived at 2 L-shaped buildings in the United States and squeezed space by less than 1/10,000th of a proton's width. And human beings noticed. Think about what that means. The universe produced these waves 7 billion years ago. It did not produce them for us. It did not know we would be here. The waves travelled across half the observable universe, through billions of years of cosmic evolution, arriving at a planet that would not exist for another 2.5 billion years after the collision occurred. And when they arrived, there were instruments waiting for them. Instruments built by a species that had only discovered gravitational waves 8 years earlier. Instruments that could measure a distortion in space smaller than anything the unaided human senses could perceive by a factor of 10 billion. The collision answered some questions and opened many more. The magnetic field mechanism explained where the forbidden black holes came from. The ring-down analysis confirmed that the merge product was consistent with general relativity, but raised questions about the merger geometry. The implications for the early universe suggested a pathway to supermassive black hole formation that models had not included. The 7 open questions remain unresolved, and the instruments that could resolve them are either still being upgraded or not yet built. The LIGO detectors will continue operating through the 5th observing run and beyond, with incremental improvements in sensitivity. The next generation detectors, the Einstein Telescope and Cosmic Explorer, are in the design and planning phases, with construction potentially beginning in the late 2020s or early 2030s. LISA is scheduled for launch in the 2030s. Each of these instruments will open new windows on the gravitational wave universe, revealing events and populations that are currently invisible. In the meantime, the data from GW2 31123 remains publicly available through the Gravitational Wave Open Science Center. Researchers around the world are continuing to analyze it, applying new waveform models, testing alternative formation scenarios, and searching for additional signals that might constrain the properties of the mass gap black hole population. Every new analysis sharpens the picture slightly. Every new event detected by LIGO adds another data point to the map. The investigation is not winding down. It is accelerating. The questions are multiplying faster than the answers are arriving, which is, historically, a reliable indicator that a field is on the verge of something significant. When the data contradicts the models, and the models are revised but still cannot capture the full complexity of the observations, and the observations themselves push the instruments to their limits, that is when the landscape shifts. That is when textbooks get rewritten. That is when what was known gives way to what is discovered. And somewhere, 7 billion light years away, in a region of space-time still gently reverberating from the most violent collision ever recorded by human instruments, a black hole 225 times the mass of our sun spins in silence. It is a Kerr black hole, as far as we can tell. It has mass and spin and nothing else. It carries no memory of the 2 forbidden objects that created it, no record of the magnetic fields that shaped its parents, and no trace of the gravitational waves that announced its birth across the cosmos. The waves are gone. They passed through us and continued onward, into the expanding universe, growing fainter with every billion light years they cross, eventually stretching to wavelengths so long that no instrument ever built could detect them. But we heard them. For 1/10 of a second, we heard them, and what they told us was that the universe is stranger, more complex and more creative than the models we built to describe it. The forbidden zone was not empty. The mass gap was not a gap. The stars that were supposed to destroy themselves completely found a way to leave something behind, and the something they left behind crashed into each other with enough force to shake the fabric of space across 7 billion light years. The pair instability mass gap was predicted in 1967. It was treated as settled science for over 50 years. And it was wrong, not because the physics was wrong, but because the physics was incomplete. Magnetic fields, the most ordinary and ubiquitous force in astrophysics, had been left out of the calculations. And when they were included, the impossible became inevitable. There is a lesson in that, and it extends beyond black holes. The history of science is filled with predictions that were mathematically correct, but physically incomplete. Models that worked perfectly within their assumptions, but whose assumptions did not capture the full complexity of nature. The geocentric model of the solar system was internally consistent. Newtonian gravity was spectacularly successful for 2 centuries. The steady-state model of the universe was elegant and plausible. Each was replaced not because it was wrong within its framework, but because new observations revealed that the framework was too narrow. GW 2-31123 is a reminder that the framework is always too narrow. The universe does not confine itself to our models. It operates according to its own rules, and our models are approximations, useful and sometimes beautiful, but always incomplete. The mass gap was a consequence of a model that accounted for nuclear physics and gravity, but neglected magnetism. When magnetism was included, the gap filled in. What other predictions are consequences of models that account for some physics but neglect others? What other gaps in our understanding will be filled when someone includes the ingredient that everyone else assumed was negligible? We do not know. That is the honest answer. We do not know what we are missing, because if we knew what we were missing, we would not be missing it. The only way to find out is to build better instruments, record more data, and pay very close attention when the data says something unexpected. The instruments are being built, the data is being recorded, and the universe, as always, is saying something unexpected. 7 billion light years away, the 225 solar mass black hole spins. It will spin for an incomprehensible span of time, gradually radiating away its mass through Hawking radiation, over trillions upon trillions of years, long after every star in the observable universe has burned out and the cosmos has gone dark and cold. It does not know that it was observed. It does not know that its birth was recorded by a species of primates on a small rocky planet orbiting an unremarkable star in an unremarkable galaxy. It does not know that its existence posed a question that took 18 months to answer and generated 7 more questions that remain open. It simply spins, and we listen. The LIGO detectors are still operating. The gravitational wave universe is still humming with signals from merging black holes, neutron stars, and potentially objects we have not yet imagined. Each signal carries information about the most extreme events in the cosmos, encoded in the stretching and squeezing of space itself. Each signal travels for millions or billions of years before reaching us, carrying with it a snapshot of the universe at the moment the event occurred. The next signal could confirm everything we think we know, or it could overturn it. That is the nature of observation-driven science. You cannot predict what you will find. You can only prepare the instruments, point them at the sky, and wait. The instruments are ready. The sky is full of signals. And somewhere out there, beyond the reach of current detectors, but within the grasp of the next generation, another pair of impossible black holes may be spiraling toward each other right now, carrying in their masses and spins the fingerprint of magnetic fields that shaped them during the death of ancient stars. When they merge, the gravitational waves will ripple outward at the speed of light, travelling for millions or billions of years through expanding space. One day, those waves will reach Earth, and when they do, if the instruments are sensitive enough, and if the models are accurate enough, and if someone is paying attention, we will hear them. We will measure the masses and the spins and the ring down tones, and we will learn something new about the universe, something that no one predicted, something that forces us to revise our models one more time. That is the investigation. It does not have an ending, it has a direction, and the direction, as it has been since the first detection of gravitational waves in 2015, is outward. Outward into the cosmos, outward into the unknown, outward into the spaces between the models, where the universe does what it has always done. It surprises us, and we listen, to appreciate what the detection of GW2 31123 means in the broader context of gravitational wave astronomy. It helps to understand just how much the field has changed in a single decade. When LIGO made its first detection on September the 14th, 2015, the signal came from a merger of two black holes with masses of roughly 36 and 29 solar masses, located about 1.3 billion light-years away. The signal was unambiguous. It matched the predictions of general relativity with extraordinary precision. The gravitational wave chirp, the rising frequency and amplitude as the two black holes spiraled closer and closer before merging was textbook. The remnant black hole weighed about 62 solar masses, meaning roughly 3 solar masses of energy had been radiated away as gravitational waves. That is a staggering amount of energy, equivalent to the total luminosity of all the stars in the observable universe, combined, released in a fraction of a second. But by the standards of what LIGO would later detect, that first event was modest. Both component masses were well below the mass gap. The spins were low. The distance was relatively close by cosmological standards. It was, in retrospect, the easy case, the gravitational wave equivalent of learning to swim in the shallow end. Over the next 10 years, the detections came faster and grew more extreme. The second observing run produced the first neutron star merger, GW170817, on August 17, 2017. That event was detected not only by LIGO and Virgo, but also by gamma-ray telescopes, optical telescopes, X-ray telescopes, and radio telescopes around the world. The merger produced a short gamma-ray burst, a kilonova, an optical glow powered by the radioactive decay of freshly synthesized heavy elements, and an afterglow visible across the electromagnetic spectrum for weeks. It confirmed that neutron star mergers produce short gamma-ray bursts and forge elements like gold, platinum and uranium, answering a question that had been open for decades. The third observing run, from April 2019 to March 2020, pushed further into unfamiliar territory. GW190521, detected on May 21, 2019, was the first event with a component inside the pair instability mass gap. At roughly 85 and 66 solar masses, the merger produced a 142 solar mass remnant. The detection was published in 2020 and immediately triggered debate about the origin of the 85 solar mass component. Was it a second-generation black hole formed through a prior merger? Was it formed in the dense environment of an active galactic nucleus disk? Was the mass gap narrower than models predicted? These questions were still being argued when the fourth observing run began in May 2023. Within months, the detectors had recorded dozens of new events, and the signal count would eventually surpass 200 for the run. Among those events was GW2 31123, but it was not the only one that raised eyebrows. GW2 50114, detected in January 2025, provided the clearest gravitational wave signal ever recorded from a binary black hole merger, allowing researchers to measure the ring-down tones with unprecedented precision and perform the most stringent tests of general relativity from a single event. The black holes in GW2 50114 were relatively ordinary in mass, making the event a benchmark for testing physics, while GW2 31123 was extraordinary in mass, making it a benchmark for testing astrophysics. Together, the two events bracketed the range of what gravitational wave detectors can reveal, from precision tests of known physics to the discovery of entirely new phenomena. The trajectory of the field is clear. Each observing run has produced detections that push the boundaries of what was known. The first run proved gravitational waves existed. The second proved that neutron star mergers forge heavy elements. The third hinted at mass gap black holes. The fourth confirmed them and provided an explanation for their formation. The fifth, expected to begin in late 2026 or early 2027, will expand the sensitivity further, and there is no reason to expect that the surprises will stop. This pattern of increasing sensitivity, revealing increasingly extreme and unexpected events, is not unique to gravitational wave astronomy. It is a recurring theme across the history of observational science. When Galileo pointed his telescope at Jupiter in 1610, he discovered 4 moons. When the Hubble Space Telescope was launched in 1990, it revealed that the universe was expanding faster than anyone had predicted, leading to the discovery of dark energy. When the James Webb Space Telescope began operating in 2022, it found massive galaxies and luminous quasars at redshifts that challenged models of early galaxy formation. In every case, the instrument revealed something the theories had not predicted, and the theories had to be revised. Gravitational wave astronomy is following the same arc, but at an accelerated pace. The field went from 0 detections to over 300 in 10 years. The mass range of detected black holes has expanded from 5 to 225 solar masses. The distances have stretched from 1.3 billion to roughly 7 billion light-years. The physics has gone from confirming general relativity in the weak field regime to testing it at its breaking point, and the astrophysics has gone from confirming that stellar mass black holes merge to discovering that forbidden black holes exist and raising fundamental questions about how the first generation of stars seeded the universe with the progenitors of supermassive black holes. All of this in a decade. The next decade promises to be even more eventful, because the instruments being planned are not incremental improvements. They are qualitative leaps. The Einstein telescope, with its 10-kilometer underground arms and cryogenic mirrors, would detect black hole mergers from the cosmic dawn when the first stars were dying. Cosmic Explorer, with its 40-kilometer arms, would observe virtually every binary black hole merger in the observable universe above a few solar masses. LISA, in space, would detect supermassive black hole mergers from the era of galaxy assembly, connecting the stellar mass events observed by ground-based detectors to the billion solar mass behemoths that sit at the centers of galaxies today. The picture that will emerge from these multi-band observations will be the first complete census of black holes across cosmic time, not just a catalogue of events but a map of the black hole population, how it evolves, how it connects to galaxy formation, how it is shaped by the deaths of stars and the conditions of the interstellar medium and the magnetic fields that thread through it all. GW2 31123 is a single point on that map, but it is a point that nobody expected to find, in a location that the map said was empty, and the fact that it exists at all means the map is wrong, or at least incomplete, in ways that are only now beginning to come into focus. The pair instability mass gap was supposed to be one of the firmest predictions in astrophysics. It was based on well-understood nuclear physics and gravitational collapse. It had been modelled, tested and refined for over 50 years, and it turned out to be a prediction about an incomplete model, not about the universe itself. The universe, as it often does, had found a way around the prediction. Magnetic fields, one of the most common and well-studied forces in nature, provided the loophole that nobody thought to check. If there is a broader lesson in the story of GW2 31123, It is this: the universe is not obligated to conform to our models. It is not required to populate only the mass ranges we predict, or to form objects only through the channels we have identified, or to produce signals that our instruments can easily interpret. It operates on its own terms, following its own physics, including the parts of physics that we have neglected, overlooked, or failed to connect. Our job is to listen, to build instruments that are sensitive enough to detect what the universe is doing, models that are complete enough to interpret what we detect, and communities that are open enough to revise their understanding when the data says something new. The detectors are listening, the data is arriving, the models are being revised, and the universe, as always, is telling us something we did not expect. There is something profoundly strange about gravitational waves that is easy to overlook when discussing the astrophysics of black hole mergers, and it is worth pausing on because it changes what the detection of GW2 3112 actually means. Gravitational waves are not like any other signal in astronomy. When a telescope captures light from a distant star, it is receiving electromagnetic radiation, photons that were emitted by the star and travelled through space to reach the detector. The light tells you about the star. It tells you the temperature, the chemical composition, the velocity, but the light travels through space without altering it. Space is the stage, light is the actor. Gravitational waves are different. They are not signals travelling through space. They are distortions of space itself. When two black holes merge, the space-time around them warps, twists and oscillates. These oscillations propagate outward at the speed of light, carrying energy away from the source. When they reach Earth, they physically stretch and compress the distance between objects. LIGO's mirrors move because the space between them literally changes length, not because a force pushed the mirrors, not because a particle hit them, because the distance between them, measured in the purest geometric sense, changed. This means that when LIGO detected GW2 31123, it was not measuring a signal from the two black holes. It was measuring the shape of space-time as directly as anything can be measured. The waveform encodes the curvature of space-time near the merging black holes, which in turn encodes the masses and spins of the objects. The ring-down tones encode the curvature of space-time around the final black hole as it settles into its permanent shape. Every piece of information extracted from the signal is information about geometry, about the shape of the universe at a specific point in space and time, 7 billion years ago. This is what makes gravitational wave astronomy fundamentally different from any other form of astronomy. It does not observe objects, it observes the geometry of the universe itself, and when that geometry behaves as Einstein predicted, as it did for GW 250114 with near-perfect precision, it tells us that our mathematical description of space-time is correct. When the geometry is unusual, as it was for GW2 310123 with its unexpected ring-down modes, it tells us that our mathematical description is being tested in a new regime. The distinction matters because it connects the astrophysics of black hole mergers to the deepest questions in fundamental physics. General relativity describes gravity as the curvature of space-time. Quantum mechanics describes the behaviour of matter and energy at the smallest scales. These two theories are the pillars of modern physics, and they are fundamentally incompatible. General relativity is a smooth, continuous theory. Quantum mechanics is a theory of discrete quantities and probabilistic outcomes. Where they overlap, at the singularity inside a black hole or at the Big Bang itself, the equations break down. Neither theory can describe what happens. A theory of quantum gravity, one that reconciles general relativity with quantum mechanics, has been the holy grail of theoretical physics for nearly a century. String theory, loop quantum gravity, causal set theory and other candidates have been proposed, but none has been confirmed by observation. The problem is that the effects of quantum gravity are predicted to become important only at scales far smaller than any experiment can probe, the Planck scale, roughly 10 to the minus 35 meters, but there is a possibility, hotly debated among theorists, that quantum gravity effects might leak outward from the singularity inside a black hole and subtly affect the ring-down frequencies observed after a merger. If the no-hair theorem is not exactly correct, if a black hole retains some quantum imprint of the matter that formed it, then the ring-down modes would deviate from the Kerr solution by a small but potentially measurable amount. The more massive and rapidly spinning the black hole, the larger the potential deviation. GW2 31123 produced the most massive, most rapidly spinning remnant black hole ever observed through gravitational waves. If quantum gravity effects exist at measurable levels anywhere, it would be in an event like this one. The current analysis found no deviation from general relativity, but the precision of the measurement was limited by the brevity and complexity of the signal. The next event of comparable magnitude, observed with a more sensitive detector, could either tighten the constraints or find the first hint of physics beyond Einstein. This is why events like GW2 31123 matter beyond astrophysics. They are not just measurements of black hole masses and stellar evolution pathways. They are probes of the nature of space-time itself, tests of the most fundamental theory we have about gravity, and potential windows into physics that we do not yet understand. The collision between two forbidden black holes, 7 billion light-years away, was not just a record-breaking merger. It was a measurement of the universe's geometry at its most extreme, and the geometry so far matches Einstein's predictions, but so far is not forever. The detectors are improving, the events are getting more extreme, and the universe has shown repeatedly that it does not run out of surprises. Every observation we make constrains the space of possible theories. Every event that matches general relativity shrinks the room in which alternative theories of gravity can hide. And every event that approaches the limits of our measurement precision brings us closer to the point where a deviation, if one exists, might finally become visible. GW2 31123 brought us closer than any previous event. The next one might bring us closer still. And one day, perhaps not in this decade but perhaps in the next, a gravitational wave signal will arrive that does not quite match what Einstein predicted. On that day, the investigation will not just accelerate, it will transform, because the detection of a deviation from general relativity would not be the end of a story. It would be the beginning of a completely new one, a story about what gravity actually is at its deepest